Yeah, therefore the measure of covariance tells us nothing beyond whether it's positive or negative or zero. The absolute number has really no meaning because an absolute number depends upon the scale of measurement. So another way of saying this is that the measure of covariance suffers from the drawback that it is not independent of the scale of measurement. Ultimately, if you are measuring the co-movement between two variables, that measure must not depend upon the units in which you have measured x and y. Right? Whatever units you measure x and y in, you must always get the same measure of co-movement. That's a problem with the covariance measure. Just like variance, covariance is nothing but a different way of looking at the variance, right? You have xi minus x bar square ke jagah pe xi minus x bar y minus y bar. So same problem will be there, right? So covariance therefore is not unit independent, it is unit dependent. Clear to everybody? This also worried an old man in the end of the 19th century. That old man's name was Pearson. Yeah, but Pearson was a very intelligent man. So Pearson said, look here, this is a common drawback, depending upon scale is a common drawback of covariance and variance because there is the same ways of doing things. So let me do one thing. He said, let me divide the covariance by the square root of variance of x and by the square root of variance of y. Okay. Now see, if I multiply x and y by alpha, this will get multiplied by alpha square. That we have seen. What will be the measure of variance get multiplied by? Alpha square again. So the square root will get multiplied by alpha. Yes. And the square root of variance of y will also get multiplied by alpha because variance of y will get multiplied by alpha square. So the numerator and denominator both will get multiplied by alpha square and the fraction will stay what it is. Right? So if you divide covariance by the square root of variance of x and the variance of y, you get a measure of co-movement which no longer depends upon the units of measurement. This measure is called the correlation coefficient. Pearson's correlation coefficient, which is nothing but covariance of x and y divided by the standard deviation of x, standard deviation of y. Covariance of x and y divided by the standard deviation of x and the standard deviation of y. It's clear? Sure folks? Okay. Now, so what is the correlation coefficient? The correlation coefficient is nothing but the covariance measure, but you have got rid of its dependent upon units. So it's an improved measure of covariance, that's all. Okay. You have learned that this measure always lies between +1 and -1. You have learned that. But did you learn why? Did you learn why? No? The Gupta Empire never taught you that. So argue why it would lie between -1 and +1. Can you be a bit louder?
We are identifying the mean of each subsequent data set and subtracting the particular average by individual elements. So we are getting deviation from the average mean item. So the other that can we consider the first variable of that particular series to be the average, I mean standard point, and can post which we can identify the deviation of first variable with respect to different deviation variables. So we can actually plot some graph similar to that, and then we can calibrate into
We want a measure of association. Yeah, that measure of association, however, whatever you do with the deviation, they always depend upon the units of measurement. So that's not going to help. In fact, we have much better techniques to do this. So, okay. So tell me, why is the maximum possible correlation +1 and the maximum possible negative correlation -1? Think of this formula and say.
Because it depends on the scale, not only.
Give me a pure formal mathematical answer where I should be able to derive that from step 1, step 2, step 3.
So in the numerator we have x minus x by y minus y. So
Just look at this formula.
in this formula, in the numerator of covariance, so that will have x minus x by y minus y. So that y minus y by the maximum value that y can take is x.
So what he says is, I think to rephrase it. What is the highest possible correlation that x can have with? Highest possible positive correlation that x can have with? With x itself. No? X cannot have a stronger positive correlation with anything than itself. The maximum possible positive correlation that a variable can have is with itself. No other variable can vary more strongly with that variable than that variable itself. Sure? So now what happens if you think of x as y? So this becomes x, this becomes x. What is covariance of x with itself? In that formula, if you replace y by x, what will you get? Variance. So what will you have in the numerator? You will have, and what will you have in the denominator? Standard deviation of x into standard deviation of x? Variance of x. So, and how much is this quantity? 1. So the highest possible positive correlation between two variables can be +1. On the same lines, argue that the highest possible negative correlation between two variables can be -1. Will be -1. Argue. What is the highest possible negative correlation between two variables will be -1. Please prove to me.
If the variance of x is -1, if you multiply the standard deviation by -1, which will also be -1 and -1.
Okay. So what he's saying is, variance of alpha x. Okay? What is variance of alpha x? Okay. So now let me find out the covariance between x and y. Okay. So look at this formula. Okay? Is equal to what? Yeah? Sure? Okay. Now, or in other words, if you look at it this way, another way of looking at it is to write this thing. Yeah? Now let us think of yi as minus xi. Okay? Then what will happen? This will become minus xi and this will become minus of minus x bar. Right? So this quantity will become minus of xi minus x bar. Sure? So this can be taken out as minus, right? So this will become minus of variance x. Sure? So the covariance formula would then become, the correlation will become, what is correlation between x and y? Yeah? Now if y is equal to -1, then this will become right? So this quantity will be -1. So therefore we have proved that the correlation coefficient between x and y will always lie between -1 and +1. So now the number has a meaning. If you say x and y have a correlation of 0.8 and x and z have a correlation of 0.3, then x and y are more strongly correlated than x and z. So numbers have some meaning now because they are now independent of the scale of measurement. Whereas for covariance, those numbers don't have any meaning. Right? They depend upon the scale of measurement, and so does the variance. Right? Very often we put too much importance to variance, but it actually depends on the scale of measurement. Right? So just like covariance, an absolute value of variance doesn't really make much sense. Right? Unless you specify the scale appropriately. How much more time do we have? Good. So is this clear? Absolutely clear, the idea of covariance and correlation. This is called Pearson's coefficient of correlation. Why Pearson's coefficient of correlation? Pearson came up. Right? Okay. Let me ask you another question. Instead of say finding Pearson's correlation of coefficient or Pearson's coefficient of correlation, the problem was the scaling. Right? Suppose I divide this by say I divide this by expectation of x and expectation of y. Covariance xy, I divide not by the standard deviation of x and standard deviation of y, but I divide covariance xy by the expectation of x and expectation of y. Will it also be unit free? Will this quantity also be unit free? Tell me what will happen to this quantity if you multiply both x and y by alpha. Yeah, we have a lot of time. Please tell me what will happen to this quantity if you multiply both x and y by alpha. Will this be unit free? Will it be? How many of you agree that it will be unit free? Please put your hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many of you think that it will not be unit free? Nobody? So what do you guys who have not put your hands up think? It's yes or no, no? Do you think this will be unit free if I say covariance xy divided by expectation x expectation y? He says yes. He says yes. Okay, suppose I multiply x and y by both by alpha, what will covariance get multiplied by? Alpha square. So this will get multiplied by alpha square. What would the expectation of x get multiplied by? Alpha. What would the expectation of y get multiplied by? So what will the denominator get multiplied by? This will cancel, no? So the resultant quantity will also be unit free. So that's another way of modifying covariance. But have you ever seen this used? No. Why is the Pearson method used and why is this not used? We don't? No, but then I could, if I don't know the exact value of expectation, I have its sample counterpart. That is, I can always write this as this is the value I know, no? And I know by my law of large numbers that actually as n becomes larger, this will get closer and closer to true as. So why does nobody ever use this? What is the problem of using this? And why not use the, why does everybody use the Pearson coefficient? Why does nobody ever use this my correlation coefficient? Yeah? Okay, so he says first, yes, unlike the -1 was boundaries, this has no maximum minimum values. There will be unit free. Right? I can't put it into boundaries, that's why. Is there any other reason?
So that there are two n's in the denominator. There will be n into n in the denominator.
Which is fine, but alpha square आएगा बाहर, so it won't matter. No, but suppose all of you are using the same data. What will the problem be? Can you think of a problem? So suppose covariance xy is positive and suppose x bar is negative and y bar is positive. What would this measure be? Positive or negative? Negative, no? So even if covariance is positive, my answer could be negative if one of the x bars is negative. If the covariance is negative and both my x bar and y bar are negative, okay, my x bar, one of the x bars is negative, I will get a positive answer. Right? So the sign will not be preserved. Right? Sign will not be preserved. To get rid of this, suppose I do this. Then that can be got rid of, but I will not get a -1 +1 boundary. Right? So the measure of correlation, what I want to emphasize with you is, there are many different ways of skinning a cat. Right? There are many different ways of doing the same thing. But some ways of doing the same thing are somehow more satisfying for various reasons. And that's why those become the formulae which you use in statistics. Right? There is different ways of reaching a destination. Some ways you have to take a longer route, some are just more convenient, more satisfying, right? And that's why they become the used methods and they come down to you as formulae. But essentially they are logically constructed because they prove certain, they satisfy certain purposes better than other ways of doing the same. Is it clear? Right? Okay. Now, is that a covariance, correlation clear? Okay. Now let me move on to a very, very important point. Now we'll begin our regression now, for which we need to first understand the idea of a conditional expectation. We have learned about expected value of x, right? Let me now talk to you about a conditional expectation. So suppose we are throwing three coins. Suppose we are tossing 3 coins. Yeah? How many possible outcomes are possible? Will there be? 8. Why? Because the first coin can land in 2 ways, the second coin can land in 2 ways, heads and tails, the third coin can land in 2 ways, so 2 into 2 into 2, 2 raised to 3, 8 possible ways of getting this. Right, so let's list those 8 possible ways. Yeah? Have I written the 8 ways? Right? Okay. Now let y be the number of heads on each toss. Let y be the number of heads. That's a random variable we are thinking. Let y be the number of heads on each toss. Okay, number 2. So what is the value for y here? Here. Here. Here, 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 right? So what are the values that y takes? 0, 1, 2. Okay. So let me write the probability distribution. Yeah? Absolutely. Now what is the probability with which x takes the value 0? 1 by 8. What is the probability with which x takes the value 1? How many times 1? 3. So you remember you are using the laws of probability. Right? These are three different outcomes, mutually exclusive outcomes. The probability of the union has to be probability of A plus probability of B plus probability of C. So you can actually now construct 3 by 2, 3 by 3 by and 3, 1 by. Right? So what will be the average value of X, expected value of Y? Zero into 1 by 8. How much is this? How much is this? What is 12 by 8? So what do you mean by 1.5? How do you interpret the number 1.5? So it says if you are tossing 3 coins and Y with the number of heads, if you kept on doing this many times, on average you should get 1.5 heads on a toss. You'll actually never get 1.5 heads on any toss. There can't be 1.5 heads on a toss. Right? Okay, but the average number of legs that a cat has in the world is 3 point something, right? Because some cats are indeed 3-legged. Yeah? So but you really find a 3-legged cat. Sure? So similarly here you will never really have 1.5, but it says, so what's this number? It's a number such that the sequence of average values of heads will converge towards as the sample size becomes larger and larger and larger. This is the unconditional expectation of Y. It is called the unconditional expectation of Y. Why? Because I can ask you the question, what will be the average number of heads on all 3 tosses given that you already have 2 heads on the first 2 tosses? Now think of a question. What is the average number of heads on all 3 tosses given that you already have 2 heads on the first 2 tosses? What is the average number of heads on the first 3 tosses given that you already have 2 heads on the first 2 tosses? So, clearly, given this information, not all points of this sample space are relevant. Is this point relevant? Yeah? No, because you have, so this point doesn't correspond to the information that the first 2 heads are taken. The first 2 outcomes are heads. Is this relevant? No, because the last 2 outcomes are heads. Is this relevant? No. Is this relevant? Is this relevant? First 2 have to be heads. So the only 2 points on the sample which remain relevant are this. So the moment I ask this question, my sample space becomes a subset of the original sample space. So the only 2 outcomes that I am now interested in is, okay, the only 2 outcomes that I am interested in is yeah. In this case, what is the number of what is the value of Y? 3. Here it's 2. So my Y can now take values 3 and 2 only. And probability of Y is what? So, if I think of Y as the number of heads on the 3 tosses, now if I think of Y as the total number of heads on all 3 tosses and X as the number of heads on the first 2 tosses, then the expected value of Y conditional upon X is equal to 2. Are you getting this? Because now I am asking the question, what is the average number of heads on all 3 tosses given that the number of heads in the first two tosses is 2. Alright? X equal to 2. What will that be equal to? Three into half plus
2 into half.
Yeah? So what is this a number of? This is the conditional mean of y given x is equal to 2. Whereas previously we thought of unconditional mean of y because we didn't impose any condition on x. Right? So you see the difference between the unconditional mean and the conditional mean? Okay. Now, if you say you do, then tell me what is the total what is the conditional mean of y given x equals 1? So given that there is one head on the first three tosses, first two tosses, what is the average number of heads on all three tosses? Given that the first two tosses have one head. Now which ones are relevant? Is this relevant? One head चाहिए ना? इधर कितना head है? 2. So does this satisfy the condition x equal to 1? No. Does this satisfy the condition x equal to 1? No. Does this satisfy the condition x equal to 1? Yes. Does this satisfy the condition x equal to 1? Yes. Does this satisfy the condition x equal to 1? Does this satisfy condition x equal to 1? Does this satisfy the condition x equal to 1? Yes. Right? So what is our new sample space? So think of the subset of the sample space, which is HTH.